3 go-to training. In day 3, this is where we talk about um, the Alex modules are related to measurements and conversions and all of the slices of the pie that should be completed by day 3. One of the most beneficial things about the go-to training um, is we get a chance to cover things that you might see in Alex that you might have some questions about. The session is being recorded. Okay, so you can always go back and look at the recorded session and say, okay, how should I do this? Or, what did I see in the go-to training that might be able to help me better understand this concept? An important thing to understand about math is that math is just a tool. Okay, it is a tool like a screwdriver or a hammer, okay, or a set of wire pliers. It's a tool that we use to make better decisions, that we use to build things. A lot of the concepts that we worked on inside of assignment 1, okay, we learned about when we were going through, I should say, day 2's Alex assignment, which deals with the percents, the fractions, and the decimals. Okay, so we had a chance to see all that stuff play out uh, there. Okay, so we're going to be looking at uh, similar concepts today with measurements and conversions. Another thing about math, besides it just being a tool that we use to make better decisions with, is math is also the study of patterns. Okay, so, a lot of times we'll find things that are fairly simple and they'll help us to deal with more complex things later on. Samuel B. Gruder, mathematician from Illinois, stated that the essence of mathematics is to take things that are complicated and make them simple, not to take things that are simple and that are easy to understand and make them so complicated nobody wants to touch it or deal with it. Okay, so that's what we're trying to do with these sessions, is just kind of go through the math and then just kind of show you uh, how the math can be better understood and how the math can be used in the real world. Okay, so we're going to start off with measurements and conversions. Okay, now we have measurements all around us. Okay, we measure almost everything you can think of. Okay, a person's height, that is a measurement of how tall they are. A person's weight, that is a measurement of their density and their mass. Okay, a person's age, that is a measurement of how much time you've been living on the planet. Okay, your grade is even a measurement of your performance in this class. Okay, so a lot of things come down to measurements. Okay, now we have different units of measurement for different things. That's why we need conversions. Okay, for instance, time. Time can be measured in days, it can be measured in months, it can be measured in years, it can be measured in minutes, and it can be measured in seconds. Okay, so what we do want to do when we are measuring things is we want to measure things with like measurements. Okay, like, if we said, well, something was 370,000 minutes old versus something was, 5,672 hours old, and we want to know which one was the oldest, then we would need some kind of conversion to convert them to like measurements. We could either convert both to hours or we can convert both to minutes. Okay, and then that would be able to let us know something a little bit more stronger about those measurements when they're converted to the same unit of measurement. Okay, and so, a minute is a unit of measurement. It's a unit of measurement for time. So is an hour. Okay, so is a foot or an inch or a yard. Those are measurements of distance. Okay, so we have a lot of measurements that we look at, because ultimately in life we want to be able to, quantify things. And why do we want to quantify it? So that we can make better decisions. If we got a guy that's 6'5" and we got a guy that's 6'2", okay, the height of those two individuals is going to give us some understanding of what they might be capable of. Now, it doesn't guarantee you anything, okay, but it does give you some understanding of what they might be capable of, as far as what they might be able to reach, you know, uh, how well they might be able to play basketball, and perhaps, whether one person might be looked at as, a more attractive leader than another person. Okay, so that's what those measurements for. We use them to help us make better decisions, but they shouldn't be making the decisions for us. Because the guy that's 6'5" and the guy 6 feet doesn't mean that the guy that's 6'5" can play better basketball just because he's taller. Okay, but it is a tool that we use to help us make the decision, but it should not be making a decision for us. That's what we got a brain for. The brain should ultimately be making that decision, and we should be looking at a lot of different factors, not just the math. Okay, so let's kind of get started. First place we're going to get started with is exponential notations. Exponential notations are very important. Our number system is a system based upon units of 10. Okay, anything that we're quantifying with our number system is based upon units of 10. Okay, to move from each place value, you're talking about a multiple of 10. Okay, so the ones place value times 10 brings you to the tens place value. 10 times 10 brings you to the hundreds place value. 100 times 10 brings you to the thousands place value. Okay, so our number system is based upon units of 10. Notice that the number system is called the decimal base number system, or the Dewey Decimal Number System. And that's because for every unit of 10, we can move the decimal 1 unit to the left or 1 unit to the right. So by manipulating that decimal, we can actually increase or decrease our place value by a base of 10. Okay. Now, right here we have exponential notations. Anything raised to the zero power is always 1. Anything raised to the first power is always itself. Those are universal truths. Okay. Universal truth is something that you can always count on. Okay, don't have to do any math with it. You can always count on it. So 5 raised to the zero power is 1. Okay, 15 raised to the zero power is 1. Anything raised to the zero power will always be 1. And anything raised to the first power will always be itself. 7 raised to the first power is 7, and 8 raised to the first power is 8. So if you can't see the power and it's just a whole number there, then it's understood that that power is going to be 1. So we have like the number 365, and if we want to write that in exponential notation, then 365 would be 365 to the first power. Okay. Now, anytime we're working with a base of 10 and we're raising it to a power, the power that we raise it to is going to tell us how many places we have to move the decimal. So if we have a positive power, then we're going to have to move the decimal to the right. Okay, as we look at that first table with the exponential notations with a base of 10, okay, we start to notice something as far as a pattern is concerned. Notice when we have a power of 0, we have 0 decimals, 0 zeros. When we have a power of 2, we've got 2 zeros. When we got a power of 4, we've got 4 zeros. And we got a power of 5, we've got 5 zeros. And we got a power of 6, we've got 6 zeros in the case of a million. Okay, math is the study of patterns. And so ultimately, we look for patterns when we're working with math so as to help us to uh, utilize the math more efficiently and effectively. Okay, uh, likewise, with the negative exponents. Notice with the negative exponents, if we have a -1, we've got one number behind the decimal. If we've got a -2, we've got two numbers behind the decimal. If we've got -3, we got three numbers behind the decimal. And if we've got a -4, we've got four numbers behind the decimal. So we've got three zeros and one. That makes four numbers behind the decimal. Okay, so that's the patterns that we want to kind of pick up and observe as we're doing the math. Okay, and the reason why those patterns are so important is because we can only do one cognitive thing at a time. Okay, so we want a lot of this math to become second nature to us so that, we can just automatically do the math without thinking about it and then free our brain up to take the math to make better decisions with. Okay, and so we said before anything raised to the zero power is one, and anything raised to the first power is going to be itself. Okay, now notice we have 10 raised to the third power here. 10 is going to be the base, that's the big number. 3 is our power. So that means that we're going to multiply three tens together. Now, because this is a base of 10, and that's our number system, we can manipulate the decimal because our number system is called the Dewey Decimal Number System, which happens to be based upon units of 10. So the word decimal and 10 are synonymous. They mean the same thing. Okay, so here we talked about our pattern. We say that, we've got a power of 3. So really what we're saying is that they're going to be three zeros behind the 1. So we've got 10 to the third power. We can take a 1, drop three zeros behind it, and that will be our answer without having to multiply 10 times 10 times 10. Okay, and likewise, we've got 10 to the negative third power. Okay, now 10 to the negative third power means that we're going to have three numbers behind the decimal. Okay, three numbers behind the decimal. So those three numbers are going to be two zeros and a 1. Okay, 1 will always be one of those numbers behind the decimal. And then we'll fill in the other places with the amount of zeros we need to get the amount of numbers behind the decimal that is representative of the negative exponent. Okay. Now, a good way of remembering this, if you got a positive exponent, your number is always going to be big because things that are positive are always big. If you got a negative exponent, your number is always going to be small because things that are small are going to be negative. Okay. So anytime we see a negative exponent, we know we're going to be talking about a number that is small, that is a decimal. Anytime we see a positive exponent, we know we're going to be talking about a number that is big. Okay, and that's going to help us out when we get to scientific notation. Okay, it's any little trick that we can use to pick up a pattern, observe a pattern that's going to allow us not to do as much thinking. We're going to be better served. Okay, so here we have a number 10 raised to the negative 7th power. I want you guys to write that in fraction form and then write it in decimal form as well. And let's see if we can come up with the correct answer for this. Okay, so we got 1 over 10 to the 7th power. And we've got 1.00000001. Or 1 to the 10 millionth. Okay, we've got 11 people in this class. Insight from others? Insight from others? Insight from others? Okay, so let's look at this. Okay, as we write it as a fraction, we can simply put it as 1 over 10 to the 7th power. Okay, now anytime you have a negative exponent, the reciprocal of that negative exponent will give you a positive exponent. So if you want to write a negative exponent, okay, as a positive exponent, you simply write it as its reciprocal. Okay, and so 10 to the negative 7th power can be expressed as 1 over 10 to the 7th power. Okay, from there we know that we are going to express that as 1 over 1 with 7 zeros, like that. Okay, and then to write it as a decimal, we know we've got to have 7 numbers behind the decimal. 6 of them are going to be 0, and then we'll have the number 1 as our other number. 6 zeros and 1 will make 7 numbers behind the decimal. Okay, so congratulations with everyone who came up with this one. Okay, and once again, as you're doing these kind of problems, you want to really be looking for patterns, things that you can observe that's going to help you to, you know, uh, cement or solidify your understanding of exponents, and especially when you're working with bases of 10 and decimals. Okay, so here we have tenth, hundredths, thousandth, 10,000th. We have 1 10,000th. Let's see if we can express this as a fraction, and then see if we can express it as an exponent. Okay, and so the exponent, okay, Noreen saying it's going to be 10 to the negative 4th power. And Joe has 1 over 1,000. Okay. Noreen also saying that it can also be expressed as 1 over 10 to the 4th power. Okay. Joe's saying 1 over 10,000. It should be expressed as 1 over 10,000. And Linnell has 1 over 10 to the 4th power. Okay, so let's look at this for a second. We've got four numbers behind the decimal here. So we know if there's four numbers behind the decimal, it's going to have to be 10 to the negative 4 power. Okay, so we can see that with those four numbers behind the decimal. Now we also know how to convert a decimal to a fraction. Okay, here we've got the tens. I'm gonna abbreviate these. Then we've got the hundreds. Then we've got the thousands. And then finally that last place value is 10,000s. Okay. So from what we've learned about expressing decimals as fractions, we know that we can look at that last place value, which is 10,000, and then that means that our answer is going to be expressed as 1 over 10,000. Okay, we're going to take that 1 there, and then we're going to look at that place value of 10,000, and then that means we're going to have 10,000 here. Okay. Now, another way we can look at this also is if we've got 10 to the negative 4 power, to write that as a reciprocal, we can simply put it as 1 over 10 to the 4 power. Like that. Okay. So it can be expressed like that as well. Now that 1 over 10 to the 4 power like that means that we've got 4 zeros behind the 1. Okay. And there we go. Okay, so there's a lot of different ways we can work out this problem. Okay. And a lot of different angles that we can look at. So when we're working with powers of 10, as in this case, we're looking at 0.053 times 10 to the third power. Now we can convert that 10 to the third power to 1,000 because we know we got 1 and 3 zeros, and then we got to multiply that by 0.053. Or we can just look at the 3, which is our power right here. And then that's going to tell us how many places we got to move the decimal. Okay, so we've got a 3 there, so that means the decimal has to be moved 3 places here, which is going to give us 53. Okay, so that's another way of doing it. Now, we can do the arithmetic and do the multiplication, or we can just simply take the power and move the decimal that many places. Okay, so here's another one. Now, with this second one, we see all those steps that are being laid out. If you don't understand the pattern or understand the steps, you can draw this out and have to do a lot of steps. But because we have a negative 4 here, that's telling us that we got to move the decimal 4 places. Now the decimal is behind the 5 here. Okay, so that's what a decimal is. It's behind the 5. Whenever you can't see the decimal, it's behind the last number. From here, we're going to have to move it 4 places. And it's not going to go 4 places to the right because it's a negative number. So that means it's going to go 4 places to the left. And we know that no matter where we're moving it, that our number is going to be a small number because our exponent is negative. When our exponent is positive, then that means we have a large number. So 4 to the left means 1, 2, 3, 4. Now those 2 places that we moved it and there weren't any numbers, we just dropped zeros in there. Okay, and so that brings us to this answer right here. Okay, now we can get away with that anytime we're working with a base of 10. And the reason why we can get away with it when we're working with a base of 10, because we said that a base of 10 is our number system, and our number system is called the Dewey Decimal Number System. So the word decimal and 10 mean the same thing. So we're multiplying by a base of 10. And when I say a base of 10, that's 10 times anything. 10 times 1,000, 10 times 10 times 10, or 10 times a million. Okay, that's a base of 10. Anytime we're multiplying by a base of 10, we simply need to move the decimal. How many numbers, how many places that number is powered to 10. Okay, so let's look at another example. Okay, here we're going to talk about scientific notation. Okay, now scientific notation is a little different than exponential notation. Where exponential notation, uh, we don't have to have, you know, other numbers. We just have to have a base of 10 and that's it. Okay, so we don't have a bunch of rules that we're working with. With scientific notation, we have a whole bunch of rules that we have to apply to it. We've got at least 2 or 3 rules. Okay. We have something called scientific notation. This is a video. I'm not going to play the video. What I am going to do is I'm going to provide you guys with the link to it. And let me see if I can copy it. Let me end the show for a second. But, if you want to watch the video, it's a really cool video. It kind of gives you guys the music and stuff to it. And so that's the link to the video if you want to see it. Okay. Sometimes it's good to look at, and watch videos and stuff like that because it just it helps us to learn something while we're having fun learning it. And a lot of times that's important because, we can spend more time learning things when they're fun and exciting as opposed to when it's boring and dry. Okay, so here's a number right here. Okay, now in order to write that number in scientific notation, we're going to have like 2 or 3 rules that we got to remember. And what I'm going to do is I'm going to kind of express those rules for you. I'm going to put an A times 10 to the B power. Okay, so A is going to be a number between 1 and 10. That's the way we're going to say it. We're going to say, okay, A is going to be it's got to be greater than 1, or we could say greater than or equal to 1, but it's going to be less than 10. Okay, so that first number's got to be between 1 and 10. It can't be like 12 or 13. It's got to be in between 1 and 10. It can be exactly 1. Okay, so we were looking at scientific notation. It could be 7.2 times 10 like that. Okay, or it could be 1 times 10 like that. It can't be 23.4 times 10. Okay, so it can't be that. So it cannot be that. Does anybody know why it can't be 23.4 times 10? Okay, what Noreen, 7.2 is more than 1. Okay, excellent. It's more than 10. You're correct. It's more than 10. Okay, 23 is more than 10. Okay, and remember our first little rule here, we said that A, which is that first number, has to be in between 1 and 10. It can't be less than 1, and it can't be more than 10. Okay, so whenever you start off with 23.4 times 10 to whatever power, that's not going to be scientific notation. Now, we can call it exponential notation, but it's not going to be scientific notation because that number's got to be between 1 and 10. Can't be bigger than 10. Okay. And then the power is going to tell us how many places we needed to move the decimal. Okay, so in this case, we will just say B. Okay, so the power is going to tell us how many places we needed to move the decimal. Okay, now we have a number at the bottom here. It says the number of molecules in 18 grams of water is, let's see, we've got our ones units, we've got our thousands units, millions unit, billions unit, uh, trillions unit, quadrillion, uh, unit, heptrillion, and septrillion. Okay, so that's 602 septrillion, 300 heptrillion. Okay, or quintillion, I think, centrillion, I think it is. Let's do this right here, right quick, because I'm a little bit rusty on that. Let's look at our unit values for a second. Let me pull it up. Okay, place value units. Okay, so let's look, see how far up we can go. Okay. And let's see if this will do it for us. I'll go right here and pull them in and let's see. Um, Millions, billions, trillions. Okay, everybody wants to stop at a billion. Place value, large numbers. Okay, I'm not a big fan of, but we'll go here. Okay, so here we go. Okay, so we've got millions, billions, quadrillions, quintillions, okay, and sectillions. Okay, so billions, trillions, quadrillion is 4, quintillion is 5, and sectillion is 6. So that was 602 sectillion. Okay. And you can see that these numbers go all the way up. And actually, one of the largest numbers we look at when we look at this is a Google is actually a number. It's 10 raised to the 100th power. And then a Googleplex is 10 raised to the power of Google, or 10 raised to the power of 10 raised to 100. Okay, so in this case, our number is going to be a sec. It's going to be a sectillion in this case. So we've got, back to it. Okay, so we've got 602 sectillion, 300 quintillion. Okay, that's a really large number. All right, so from here we got to figure out how many places we have to move the decimal. Okay, now the rule says that we can only have one number in front of the decimal. Okay, or that number's got to be between 1 and 10. So we're going to move it 3 places there, 6 places, 9 places, 12 places, 15 places, 18 places, 21 places, and 23. So we had to move it 23 places to get to a number that is between 1 and 10. Okay, so we had to move it 23 places to get to a number that is between 1 and 10. Okay, the number can't be smaller than 1 and it can't be larger than 10. Okay, so 6.02, if we stopped at 60, then that number would be larger than 10 and it wouldn't work, wouldn't be scientific notation. So then we're going to multiply that by 10, and then the amount of places we had to move the decimal was 23 places. And we see that Noreen was, way ahead of us in her calculation. So, she can be our resident or local expert when it comes down to scientific notation. Okay, so that's our answer. 6.023 times 10 to the 23rd power. Okay, so here's the mass of electron. I'm not going to try to state this number, okay? But what I'll do is I'll give you guys an opportunity to see if you can write it in scientific notation form. Okay, so we got some pretty good answers so far. 9.108 times 10 to the negative 28 power. Okay, we got a few people in this session, so what does everybody else think? Okay, excellent. Okay, and once again, the absolute value of that number, that first number has to be in between 1 and 10. Okay, so in this case, we can stop at 9.108, because that is in between 1 and 10. And then that's going to be times 10 raised to the negative 28 power. Okay, now, we can say, well, we moved the decimal 28 places to the right, but anytime we're working with a small number, we know our power is automatically going to be negative. So anytime we're working with a small number, our power is automatically going to be negative. Anytime we're working with a big number, our power is going to automatically be positive. Okay, and so with scientific notation, we'll always have one digit before the decimal place. That one there, 1.9. And of course, the power is going to tell us how many places we needed to move the decimal. Okay, so if we moved it 2 places from the 1.9, that would give us 190. We have 2 numbers at the bottom down here. Okay, now neither one of these numbers at the bottom are in scientific notation form. They're in exponential notation form, but they're not in scientific notation form. Does anybody know why neither one of these numbers are in scientific notation form? That is correct. Uh, that is correct, Noreen and Joe. You guys said the same thing, and you eloquently said it in different ways. But that is correct. The first one is a no-go because it is less than one, or we can say that there is not one digit in front of the decimal. The second one is a no-go because it is greater than 10, or we can also say that it has more than one digit in front of the decimal. So neither one of those numbers are in uh, scientific notation form. Okay. Now, can I ask you guys a question? Can we find a way to write these numbers in scientific notation form? And if so, how? Okay, not sure. That's an honest answer. Okay, how about everyone else? Okay, so Jesus said that we could rewrite them, just take away an exponent. Yeah, Jesus, you're correct. We could do some manipulating. We could definitely do some manipulating. Yeah, we could definitely do some manipulating. We could take that 0.19 and say we're going to write that in scientific notation form. How will we write 0.19 in scientific notation form? Okay, so we're just going to focus in on that 0.19. We're not going to worry about the 10 to the third power right now. How can we take that 0.19 and write it in the scientific notation form? Okay, so starting off with 1.9 is a good start, Joe. What else will we need to do? Okay, so we got that 1.9. So what else would we need to do after we got the 1.9 to finish writing the 0.19 into scientific notation form? How many places do we have to move the decimal to get to 1.9? One, that's correct. So we would say times 10 to the negative 1 power. And then, of course, we would just still bring down the times the 10 to the third power. Okay. So see how we took that 0.19 and wrote it in scientific notation form by simply moving the decimal one place to the right, and then that gave us 1.9. And then we said, well, how many places do we have to move that in order for that to occur? It was one place. So we made that times 10 to the negative 1. Okay. Now we're still not finished. Okay. Because we can take this right here And we're going to use a rule called the product rule. And the product rule says that anytime we multiply two exponents with the same base, we're going to add the powers. And so we're going to come out with 1.9 times, and we've got that -1 plus 3 will give us 10 to the second power. Okay, so and this is what Joe said at the beginning when we were talking about this. Okay, he actually came up with this as an answer. So good job, Joe. Okay, so that was 1.9 times 10 to the second power. All right, what about the 24.5? How could we take 24.5 and write it as scientific notation form? Okay. And all we're going to do at the beginning is just focus in on the 24.5. We're not going to worry about the 10 to the 25th power. Okay, so we're going to say 2.45. And that's going to be times 10. And that is correct, Jesus. That's going to be 10 to the first power. Okay. And the reason why you want it to be to the first power, because 24.5 is a big number. And anytime it's a big number, the power has to be positive. Now, 0.19, which is like 19 cents, is a small number. And anytime it's a small number, uh, the power has to be negative. So because this is a big number, 24.5, it's going to be a positive power. Okay. And when we talk about in reference, if you want to say, well, what are you referencing for it to be big or small? Just the number one. Because anything to the first power is going to be anything raised to the zero power is one. So we use one as our reference point, just like zero is our point of origin. So, if it's larger than one, then that means that you're going to be working with a positive power. Okay. If it's smaller than one, like 0.19 or 0.75, that means you're going to be working with a negative. Okay. And then, of course, we're still going to have times 10 to the 25th power. And we're going to use that product rule again. Okay, now the product rule says that anytime the bases are the same, we add the powers. Okay, so we're going to say 25 plus 1 will make 26. Okay. Okay, you guys excuse me. I want to apologize for that. My phone, I thought I put it on vibrate. Apparently didn't do that. All right, so there we go. It's on vibrate. I'm sorry about that. Okay, so those are going to be our new answers written in scientific notation form. 1.9 times 10 to the second power, 2.45 times 10 to the 26th power. Once again, in order for it to be in scientific notation form, that first number has to be between 1 and 10. If it's not between 1 and 10, it's not in scientific notation form. It's in exponential notation form. Okay. Scientific notation form is a very important way of notating numbers. And it's called scientific because we use it in science to reference things that are really large and to reference things that are really small. Okay, like atoms, okay, and the size of the sun. Okay, like our sun is 1 billion times larger than our Earth. But the largest sun known to mankind is a billion times larger than our sun. So the largest sun known is a billion times larger than the Earth. And I'm going to clean this up by coming back into it. Okay, and so those are not in scientific notation form. Okay, so we got, just for a little extra practice, we've got two numbers here, the diameter of the planet Mercury in terms of miles. And then we've got the average distance to the sun in terms of miles. And I want you guys to write both of those numbers. They're in standard form right now. We call it standard because it's the standard, the way we average or traditionally write numbers. I want you to take both of those numbers and write them in scientific notation form. Okay, let's see. We've got 3.1 times 10 to the third power. And we got 3.6 times 10 to the seventh power. Okay, how about everyone else? Okay, we got 3.1 times 10 to the sixth power. Okay, so let's take that 3,100. Okay, how many places do we have to move that decimal in order to get just one number in front of the decimal? Okay, and that is correct, Joe. We'll just move it three places. Okay, we'll just put the 3.1 like that. And that's going to be times 10. Now, is that power going to be positive or negative? Is it going to be a positive 3 or a negative 3? Okay, that is correct. It's going to be a positive 3. Now, why is it going to be positive and not negative? Why is it positive and not negative? Big number. Excellent, Vicky. Big number. Okay, 3,100 is a big number. And so since it's a big number, our power is going to be positive. If that was a small number, then our power would be negative. Okay. And when we're talking, when we're referencing big or small, we're referencing it to the number one. Okay. So the number 36 million. Okay. How many places we're going to have to move that decimal to get one digit in front of? And that's going to be 7. Okay. So is that going to be a positive 7 or a negative 7? Positive. Yep, that's correct, Lionel. Positive. And why is it positive and not negative? Excellent, Joe. Big number. It's a big number. Okay. So big numbers are going to give us positive exponents. Small numbers are going to give us negative exponents. So you guys are doing super job with the scientific notation stuff. Okay, now scientific notation is one way we measure things. Obviously, scientists use scientific notation when we're trying to measure uh, things in science. Okay. Uh, we can also take things and write them in standard form using scientific notation. And of course, we're just simply moving the decimal by the amount of powers that we got. So we got 12, raise something to 12 power, we're going to move the decimal 12 places. Okay, and if that's a positive 12, then that means that's going to be, 12 places to the right so that we can get a big number. If it's a negative power, we're going to move it 3 places to the left so that we can get a really small number. Okay, so if we wanted to write this number in scientific notation form, we're going to have to move the decimal 2 places to the left. And we know no matter how we move it, we know that our power is going to be positive because 125.6 is a big number. Okay, and so, if it's a large number, your power is going to be positive. And so at that point, it's just a matter of, how many places did I have to move it? Did I have to move it to the left or did I have to move it to the right? How many places? Okay, so here we're going to have to move this one to the left. Okay. Okay. Now when we move it here, one of the things that we got to understand is that we're having to take away a place value. So since we're having to take away a place value on one end, we're gonna have to add it on the other end. Okay. Or we can just simply go 32.5 like that, and we say, well, okay, that's a big number. So that's going to be 3.25 like that times 10, and then that's going to be a positive one because that's a big number. And then if you multiply the 10 to the third, that's on the back end of that. We've now got 4 of those. Okay, so we go 3 plus 1 makes 4. Okay. Okay, so we're ready to move forward into the customary and the metric. Okay, now we've had a glimpse of the customary and the metric when working with assignment 1. Okay, we were asked to make some conversions. Okay, dealing with feet and dealing with meters. Okay, in order to complete assignment 1. Okay, we had to do some increasing and decreasing. Okay, so the customary system is a system that we use here in the United States, and it's also used by 2 or 3 other countries in the world. About 90% of the world uses the metric system. Okay, the customary system uh, heavily relies on fractions. Okay, because you have a lot of different conversion rates that you have to work with the customary system. With the metric system, it heavily relies on decimals because the conversion rate is always a base of 10. Okay, and we said that decimal and 10 mean the same thing. Okay, so all those areas in the gray that you see in the map, they use the metric system. All those areas in the red you see on the map, they use the customary system. Okay, so the United States, Liberia, and Myanmar are the only places that use the customary system. Now, even in the United States, we use customary system for things like medicine and food and beverages. Okay. So here we have uh, some different quantities. We've got length, we've got mass, we've got temperature, we've got volume and time. And then we get a chance to see how the customary system measures those quantities. And we get a chance to see how the metric system measures those quantities. Obviously, by looking at these tables, we can see that the customary system has more units of measurement for these different quantities than the metric system does. Okay, for instance, when we were working with the length uh, in our assignment one, we had to use two conversion rates. We had to use one for feet and we had to use another one for inches. Okay, versus when we were working with the meters, we only had to round the meter to the nearest hundred. So, once we did our increase by 24% and we were working with meters, we just simply had to round to the nearest hundred and we were finished. When we increased by 24% with the customary system, we found ourselves having to convert, those fractions of a foot to inches, which created a challenge, to say the least. Okay, so when we look at our metric system here, we're looking at our base. Okay, our base for length is going to be meters. Our base for mass is going to be grams. And our base for liters is going to be volume. Okay, so those are going to be our bases. And then with the bases, we're going to have uh, prefixes, which are going to be, bases of 10. So to go from meters to decameters, you multiply by 10. To go from meters to hectometers, you multiply by 100. And to go from meters to kilometers, you multiply by 1,000. To go from meters to decimeters, you divide by 10. To go from meters to centimeters, you divide by 100. To go from meters to millimeters, you divide by 1,000. So if we've got like 700, centimeters, and we want to convert that to meters, we would divide by 100, and then that would give us 7 meters. Now we're going to use a ladder approach to help us do those conversions a whole lot easier. Plus, we're going to use a mnemonic. Mnemonic is just a fancy, catchy way of saying something to help us to remember these prefixes and how we convert from one to the other one. Okay, now here's our mnemonic. King Henry died Monday drinking chocolate milk. Okay, and King stands for kilo, Henry stands for hecto, Di stands for deca, Monday stands for main, Deci stands for drinking, Centi stands for chocolate, and Milli stands for milk. Okay, and so we'll use that sort of like we use a step-step process to convert from one unit measurement to the next unit measurement. Okay, and once again, here's a comparison, helping us just have a reference that it takes 100 centimeters to make a meter, and that it takes 1,000 meters to make a kilometer. Okay, and so and the reason why it is because it takes a whole lot of something small to make up something big. Like, and a good way of referencing it is just to think about money. Okay, um, if you've got three $100 bills, they're bigger, but it takes a whole lot more dollars to make up those three $100 bills. It takes three $101 bills to make up three of those $100 bills. Or another way of looking at it, if you had, say, three $20 bills, it would take 60 $1 bills to make up three $20 bills. And that's because the $20 bills are bigger. So when something's bigger, it takes less of it than of something smaller. Okay. Using money as a point of reference, you can always, if you're working through it and you kind of forget the rules or kind of forget the way, the conversion should be going, you can always go back to something you're familiar with, like money, and just reference it to money, and it'll give you more insight to what you should be doing. Okay. Here's that stair-step process that I was talking about. Okay. We're going to start with the king, you know, for K, and then we're going to go H, D, M, D, C, M. Okay. And so it's a stair-step process, and we can actually we can see that stair-step process right here. Okay. And we can just start anywhere on the stair and then convert to the next unit. So let's say, for instance, if we got 300 centimeters and we want to convert it to meters, and then we need to know if we're going to move the decimal to the left or the right. So what we'll do is we'll simply put 300 right where the centimeters are right here. Okay. And where we've got to go is to meters, because that's what we're trying to convert to. And so meters is going to be your main measurement. So that's where we're trying to go. Okay. And so as we go from centimeters to meters, we're going to notice that we're going to be going to the left. So we can see that we're going to the left as we're doing that. And so for each move, we'll move the decimal 1 unit to the left. Okay, so notice that we went to 30. Okay, and we went to 30 because we started off with 300 like this. And then, of course, the decimal's back here. And so then we moved the decimal 1 place. And then that gave us 30 like this. So that gave us 30 like that. And then we're going to move it 1 more place to get to the meters. And then that's going to give us 3. Okay, so anytime we're converting from 300 centimeters to meters, that's going to give us 3 meters. Okay, that's going to give us 3. Okay, and so that's why, that stair-step process is really good. So if you can just remember King Henry died Monday drinking chocolate milk, and then you set that up in a stair-step process, then you can just use that stair-step process to convert from whatever you want to convert to. Okay, so here's another one. So we're going to say 9 kilometers. Okay, so now if they're wanting us to go from 9 kilometers, kilograms to centigrams, we're going to start up here with the kilograms, and then we're going to end up way down here to the centigrams. And so we can see from going from there to there, we're going to the right. So for each unit, we're going to move it to the right. Okay, so we're going to start off with 9. And then for each one, we'll move it to the right, the decimal to the right 1. So that moving it 1 to the right is going to give us 90. 1 more to the right is going to give us 900. 1 more to the right is going to give us 9,000. 1 more to the right is going to give us 90,000. And 1 more to the right is going to give us 900,000. Okay, so to go from 9 kilograms to 900 centigrams. So that's the equivalent. But the beauty of this stair-step process is it kind of makes it fun, and it takes all of the guesswork up out of it. Yeah, Joe, that's correct. The main is the gram. Okay, and so anytime whether we're working with grams, uh, liters, or meters, the main will either be one of those 3: liters, meters, or grams. Of course, grams is mass, uh, liters is volume, and meters is distance. Okay, and this is, a little math humor. I got you 10 roses. I believe strong relationships are based on the metric system. Metric system is such a strong system because it's based upon units of 10. I mean, we can obviously see that, if you're converting from centimeters to meters, that base of 10 times 10 is 100. So that's what makes it so much uh, easier to work with. And because we're working with a base of 10, we're obviously just going to be moving decimals around. Because remember when we first started, we said that, you know, a base of 10 and our decimal system, Dewey Decimal System, they mean the same thing. Our number system is based upon units of 10, and we call our number system the Dewey Decimal Number System. So when we're working with base of 10, we simply have to move the decimal around. Okay, so when we're looking at area conversions, anytime we're figuring out the area of something, it's always going to be a square unit. Okay, notice that we got that square there. Okay, so anytime, make sure you put the square. I don't know about other classes, but I had, one or two people that didn't put the square, and unfortunately, the problems had to get marked wrong when that occurs. Okay, we got to make sure we got the right unit of measurement. Anytime we're talking about area, it's always going to be square. Okay, and so if we wanted to convert from centimeters to millimeters, the first thing we would have to do is convert the centimeters to millimeters. Okay, and so it's going to take, for every 1 centimeter, there's 10 millimeters. Okay, so that's the way we would have to convert centimeters to millimeters, and then we would have to multiply. So it'd be 10 times 10 in this case. So we converted 1 centimeter to 10 millimeters, and then we converted the other 1 centimeter to 10 millimeters, and then we multiply, and then that gave us 100 squared millimeters. Okay, so here's a problem right here. It says a rectangle field is 34 kilometers long, and I'm sorry, not 34, but 3,400 kilometers long and 2,600 kilometers wide. What is the area of the field in square meters? Okay, so I'm gonna let you guys see if you can solve this problem, but I am gonna give you a hint. In order for you to solve this problem, you got to convert the kilometers to meters before you can figure out what the area is. Okay, let's see. Jesus has 88,400 square meters. Jesus, how did you convert the kilometers to meters? Okay, so you moved the decimal 3 places to the right. Okay. Did you use that stair-step process? Or did you just know that, okay, Okay, so you use the step process. Now, some people automatically know the conversion rate. The conversion rate from kilometers or kilometers to meters is 1,000. Okay, and so we know that all of our conversion rates are going to either be 1,000, 100, or 10. Okay, and so Joe also came up with 88,400 square meters. Okay. All right, so we're going to go ahead and look at this one in the interest of time. Okay. Obviously, as Jesus and Joe has pointed out, we've got to convert first. Okay. Where you can use the stair-step process, or you can also just come to a better understanding of what the conversion rates are. The conversion rates are always going to be a base of 10, so they're going to either be 1,000, 100, or 10, depending on what you're converting to. Okay, and then it could also be 10,000, depending on how far away from whether you're converting to the main, which is the meters, the grams, or the liters, or if you're having to convert all the way like from a kilometer all the way to a millimeter, then that's going to be like 1,000 times 1,000 to get that conversion. Okay, so we're going to first do the conversion. And so point 34, we'll move it 3 places to the right on our stair step. And then we're going to move to point 26, 3 places to the right for our stair step. And then that's going to give us 340 meters times 260 meters. Then we're going to multiply together. And then that's going to give us 88,400 square meters. Okay, so good job. And Joe, thanks for giving us that insight into where that prefix kilo was derived from. Okay, so here's some customary conversions. Okay, a cook needs 1 quart of milk for a recipe. How much is this in cups? Okay, so we got to go from uh, quarts to cups. Okay, so the first place you're going to look is, okay, this is where you are right here, the quarts. So you got to move from that 1 quart, 2 pints. Okay, and then from the pints, you got to go to the pints to get to the cups. Okay, and so that's going to be the process. Okay, so you're going to go from 1 quart equals 2 pints. And then, if you want to convert the pints to cups, then we know that we had 2 pints. So we're just going to multiply 1 pint by 2 to come up with 2 pints here. And then if we multiply that by 2, we'll multiply this by 2 to come up with 4 cups. Okay. And that's because we started off with 1 quart, but 1 quart is equal to 2 pints. And so when we go to our next conversion, we know that still has to be 2 pints. And so 1 times 2 brings us back to the 2 pints. And then if we've got 2 cups, we have to multiply that by 2 as well. Okay. The most important thing to remember with these conversion rates is that that rate has to be maintained. That ratio, that rate, that relationship has to be maintained. Okay. And so we went from 2 pints, and then 2 pints equals 4 cups. Okay, so here's some other conversions rates that we're going to have. Okay, the biggest part is just understanding the conversion rate, whatever it might be, and then you'll end up either multiplying or dividing by the conversion rate, whether you're trying to go one way or the opposite way. Okay, for instance, This problem says, how many centimeters are there in 4 inches? So we're going to have to figure out what the conversion rate is for inches. And here it is right here, 2.54. Okay, so that's the conversion rate, 2.54. 1 inch is equal to 2.54. So we want to know how many centimeters are there in 4 inches. So to figure that out, we're going to take the 2.54, we're going to either multiply it by 4 or we're going to divide it by 4. What do you guys think we should do? Do you think we should divide it by 4 or multiply it by 4? Okay, multiply. And why do you guys say multiply? Okay, that's correct because to go from the 1 inch to the 4 inches, you had to multiply by 4. 1 times 4 gave you 4 inches, so you have to do the same thing to the 2.54. You also have to multiply it by 4. Okay, the relationship between these conversions is is similar to the relationship that we see with fractions. Okay, so the same thing you see with fractions, like if that was 1 over 2.54, then you would have to multiply the top and bottom by 4 to get to your next conversion. Okay, so if you take what we know about fractions and use that, it'll be a solid foundation to build on as we're using conversions. Okay, so we're gonna end up multiplying by 4 in this case. Okay, so that's a good point, Jesus. And then so our finance is gonna be 10.16 centimeters. Okay, now if we have uh, if there are 25 centimeters and we want to know how many inches that is, okay, we're still going to have to use that same conversion rate. So in this case, we're going to use that same conversion rate. And so to figure it out, we're going to have to divide. So we're going to take 25 and divide it by 2.54. Okay, and then that's going to give us 9.8, approximately 9.8 inches. Okay. Always remember this with the conversion rate. You'll always end up multiplying by the conversion rate or dividing by the conversion rate. What can I ask you guys a question? If we don't know what the conversion rate is, how can we find it? If we don't know what the conversion rate is, how can we find it? Let's say if we wanted to go from meters to yards and we didn't know what that conversion rate was, how would we go about finding it? Excellent, Noreen. Excellent. Google it. We got Google on our phones. We can always Google if we're trying to convert from another rate to the next one. I had to go out and buy some screws for my TV because the stand got broke, and so the specs that which is what they call it, the specifications, the length and the diameter, with the manufacturer provided was in the metric system. But when I went to Home Depot, everything was customary, it was all in inches. So what I did was I Googled the conversion rate from millimeters to inches. Okay. And then that allowed me to find something that was close to what I was looking for. Okay. We can always Google and figure out what the conversion rate is. Now, if you know what the conversion rate is, then you can convert anything. But that's the trick, knowing what the conversion rate is. And we can always convert by either multiplying or dividing. Okay, so here we've got one. We've got clothes is A cloth is 39 inches long. How long is it in feet and inches? What is the conversion rate from inches to feet? What is our conversion rate? 12. That's right. Correct. 12. So 12 is a conversion rate. Okay. Whether you're going from feet to inches or whether you're going from inches to feet, 12 is going to be our conversion rate. So if we've got 39 inches and we want to convert that to feet, we'll divide by 12. If we've got 7 feet and we want to convert that to inches, we'll multiply by 12. Okay, so that's always the kicker, figuring out what the conversion rate is. In this case, 12 is our conversion rate. Okay, so we're going to take the 39 inches, divide it by 12 to figure out how many feet we have. Okay, if we take 39 divided by 12, we can pull 3 feet out, and then we have a quarter of a feet. Now that quarter of a feet can be converted back to inches by multiplying that by 12. So we take 0.25, multiply it by 12. That'll tell us how many inches we have. So we'll have 3 feet and 3 inches, I want to say. Okay, and so our final answer is going to be 3 feet and 3 inches. Okay, now, we can multiply by a quarter. We could also use long division on it. We could take 12 and divide it by 39. And here's our long division here. And then it's going to tell us, what do we have remaining in inches? 39 inches remaining. And we were able to pull out 3 feet. Okay, so if we have a wall that's 174 inches, and we want to convert that to feet and inches, okay, you guys tell me how many feet and how many inches will you have if you converted the length of the wall, which is 174 inches, to feet and inches. Okay, so let's see, we've got 14 feet, 6 inches. Okay. Okay, so what's gonna be our conversion rate here? 12, that's correct, 12. So we'll take 174, and in this case, we'll divide it by 12. And that's gonna give us 14 feet, point 0.5. So it's gonna be 14.5 feet. Now that 0.5 is not inches. That's a half of a foot. Okay, and then if we wanted to figure out how many inches that's going to be, we'll take 0.5, correct, Noreen, and multiply it by 12. And that will give us the 6 inches. So in the end, we'll have 14 feet and 6 inches. Okay, and then this is just a little concept to help us to understand when we're looking at this is going to move us into geometry, just to help us understand that, just looking at things naturally, which is, estimating and rounding are really favorite tools of people who don't really like to do a lot of math. And so they try to avoid the math, instead of actually doing the measurements. Okay. And I've been guilty of that a few times. I'll try to put something together and I don't really want to pull out, my measuring stick and, do the math the correct way, but sometimes that doesn't turn out well when you take the shortcuts. Okay. And that's all these pictures are trying to help us to see. All right. So that kind of stuff right there is just break time stuff. And now we're going to move off into some geometry with the time that we have left. We got about 25 minutes left. Okay. And with geometry, typically when we start off with geometry, we normally start off with, a point. And a point, has no breadth, no width, or no depth. And then from a point, we go into what's called a line segment. Okay, and let me put some of those things down. Okay, that's a point right there. Okay, that's the most basic concept in geometry, which is a point. And then from a point, we go to a line segment. Put a point on the end of this one, and a point on the end of here. And then from a line segment, we go into a ray. A ray has a beginning but no end. And it can go in either way. And then from there, we go into a line. Okay. And these are, the four most basic concepts in geometry: a point, line segment, ray, and a line. Okay. And almost all of your other concepts are derived from these concepts here. Okay. For instance, an angle is two lines or rays. Okay, we can see it right here, formed by two lines or rays, and they diverge at a common point, okay, which we call the vertex. Okay, so if we have, let's see something like this. Okay, and that common point right there, we call that the vertex. Okay, that's where they meet up at the corner. Okay, and then of course that's two rays. If you broke it apart, you would see that it was actually two rays. Now we use a protractor to measure angles, okay, and we can measure angles in terms of degrees or radians, okay. The one that seems to be the most popular are degrees, okay. Like, if something goes full circle, that's 360 degrees, okay. We have some special names for angles when we're working with them. Here we have what's known as a quadrilateral. It's a quadrilateral because it's got four sides. The word quad means four. Okay, and then each angle, here we can look at it. We can see that each angle here has a degree to it. Okay, and so if an angle is less than 90 degrees but greater than 0 degrees, we call that an acute angle. So that's what angle C is. An obtuse angle is more than 90 degrees but less than 180, like angle B. And then we have a right angle, which measures exactly 90 degrees. That's angles A and D. Other angles that we'll see will be supplementary angles. Supplementary angles is when you add both angles together, they equal 180 degrees. And complementary angles is when you add both angles together, they equal 90 degrees. Okay, so if we have an angle measures 54 degrees and we want to know what is that measure of its complement, the first thing we got to know is we got to know what a complement is. Okay, and so we said our complement is when angle A and angle B When we add them together, they equal 90 degrees. So that's what that word complement means. Now, if we already know what one of the angles are, let's say we already know what angle B is. We're saying that angle B is 54 degrees. Now, what we got to do is figure out what that other angle is. Now, we can do that by subtracting 54 degrees from 90. So we can say angle A is going to be equal to the 90 degrees minus the 54 degrees. So angle A is going to be equivalent to 36 degrees. Okay, so that's the way we can do it. Now we can also just say, well, okay, 54 plus what will give us 90 degrees. But in order to solve this problem, the most important thing is understanding what a complementary angle is. Okay, if we got that part, the rest becomes easy. If we don't got that part, then we struggle with it. Okay, let me clean this up. I was hoping I could pull them on different pages. Okay, so here's one that I want you guys to see if you can do. If an angle measures 112 degrees, what is the measure of its supplement? Okay, 68. Okay. Okay. And what is the key word here or the key concept to let us know how to solve this problem? So what's the key word that kind of tells us what we need to do? Supplement. That's correct, Noreen and Jesus. Supplement. Okay, that word supplement lets us know that we're talking about two angles that you add together to equal 180. Okay, so that's the key word, supplement. Okay, and so we're going to take 180 minus 112, and then that's going to give us 68 degrees. Okay, and those two angles added together, 68 plus 112, will equal 180 degrees. Okay, so we've talked about acute angles, we've talked about right angles, we've talked about obtuse angles, we've talked about supplementary angles and complementary angles. Okay, there's going to be some other angles that we're going to need to look at because they've got special properties. Okay. Uh, Now with supplementary angles, they're just adjacent to each other. Okay, other angles that we'll see will be vertical angles. Okay, vertical angles will equal each other. Okay, and so when we look at this transversal here, angles 1 and 6 are vertical. So that means they have the same degrees. If one of them's 50 degrees, the other one's 50 degrees. Okay, vertical angles are non-adjacent angles, but they share the same vertex. Okay, so they share the same vertex. Okay, and so we're not going to do the light up geometry. From here, we'll look at polygons. Okay, polygons are closed plane figures bounded by straight lines. Polygons have 3 or more sides to them, and all the sides are straight. We have regular polygons, and all their sides and angles are equal in measure. And then we got other polygons. Okay, some other polygons we might see as a triangle. Okay, and the reason why a triangle is not a regular polygon we do have a triangle that is a regular polygon. That's called an equilateral triangle. But then we've got triangles like scalene triangles and, obtuse triangles, okay, and isosceles triangles that are not all the sides and the angles are not equal to each other. So only the equilateral triangle is a regular polygon. All these other triangles are just other polygons. A quadrilateral has four sides to it. Okay, we've got like rectangles, we've got rhombuses and kites and trapezoids. Those are all quadrilaterals and other polygons. Now we do have one quadrilateral that is a regular polygon, and that's a square. So a square is a regular polygon. We got pentagons, they're five-sided polygons. Hexagons are six-sided polygons. Heptagons are seven-sided. Heptagon is seven. Octagon is eight. Nonagon is nine. Decagon is 10. Here are the regular ones, which are different than the other polygons we just talked about. We talked about, an equilateral triangle being a regular polygon and a square also being a regular polygon. We also have a regular pentagon, a regular hexagon, a regular heptagon, a regular octagon, nonagon, and a decagon. Okay, so all of those are also polygons. Okay, some triangles that we'll look at. Okay, and I referenced some of these triangles when I was talking about other polygons. Like I said, a scalene was not a regular polygon, and that's because none of the sides have the same measure. And I also referenced isosceles. Isosceles has at least two sides that have the same measure. Okay. And then there's an equilateral. All sides and all angles have the same measure with an equilateral. Okay. Now, an equilateral triangle is also an isosceles triangle. So that's important to know. All equilateral triangles are isosceles triangles as well. But not all isosceles triangles are equilateral triangles. Okay, triangles can also be classified by angles as acute, obtuse, or right. Okay, here's a right triangle. It has an angle that is 90 degrees. Here's an obtuse triangle. It has an angle that is more than 90 degrees, or less than 180. And here's an acute triangle. It has angles that are less than 90 degrees. Okay, something that is important to remember about triangles is the sum of the interior angles of all triangles add up to be 180 degrees. So if you got a triangle, all three of those inside angles are going to add up to be 180 degrees. Okay, so here we have a triangle. And when we look at the interior angles here, we've got 35 degrees, 115 degrees, and 30 degrees. When we add up all three of these degrees, they will equal 180 degrees. And if they don't equal 180 degrees, it's not a triangle. Okay, and the same here. 50 plus 50 is 100, plus 80 makes 180. Okay, so here we've got to figure out what is that last angle that's going to allow all three of them to equal 180. Okay, so all the angles have to add up to be 180. That's just a math rule, can't get around it. Okay, so we're going to say angles 50 degree angle 70 degrees. We're going to add those two together and come up with 120 degrees. I will subtract that from 180, and that'll give us 60 degrees. So that last angle equals 60 degrees. Now we could say, 50 plus 70 is 120, and then we can say 120 plus 60 equals 180 degrees. With our quadrilaterals, there's a lot of them. Okay, they have four sides. One type we'll come across is the parallelogram. Okay, we can see a parallelogram here. Two parallel sides. A rectangle, all right angles. A square has all right angles and all the lengths are equal. A kite has two pair of equal adjacent sides. A rhombus, all four sides are equal in length. A trapezoid, it has two sides that are parallel, and these are called the bases of the trapezoid. Okay, so we can see that there. Besides the polygons, we also have the polyhedrons. These are three-dimensional. They're solid. Okay, we got a prism. We have pyramid. We got a cone. We have a cylinder. And we have a cube. When we look at polyhedrons, they have faces. The face is the flat surface. They also have edges. That's where two faces meet. And then they have a vertex, and then that's where the three faces meet. We're not going to look at that animation that Pixar. Okay, one-dimensional is perimeter. Two-dimensional is area when we're looking at polygons. Three-dimension is volume when we're looking at polyhedrons. Okay, so the way we calculate the perimeter is we add up all of the outsides. So we just look at the length. So we just add them all up. The way we figure out the area is we multiply the length times the width, or the height times the base. And that's how we figure out the area. The area is always going to be squared. The perimeter won't. And here's some formulas that we'll need to know. Formula for a square or rectangle, formula for a parallelogram, formula for a triangle, and then formula for a trapezoid. Most of these formulas are similar to each other. Inside of the LMS platform, there is a formula sheet that you can use. You can pull it down and just use it. Okay, notice how we took that parallelogram and we cut it in half, and that's how it looks like a triangle now. So half of a parallelogram is a triangle. All right, here we have some problems where we're asked to find the perimeter and area of the square. Be sure to write the correct unit in your answer. Okay, so I want you guys to see if you can find the perimeter of this square, and then see if you can find the area of the square as well. Okay, and what formula did you guys use to find the perimeter? How did you guys come up with that formula? Okay, 4 times 26. Okay. What about the area? Okay, 676 square yards. Okay, and we just said 26 times 26, the length times the width. Okay, we also could have just said 26 squared or S squared. Either way, it would have given us the same answer. Okay, so great job. Okay, so here's another problem for us. The area of a rectangle garden is 6,600 feet. Okay, so that's the area of the rectangular garden. If the length of the garden is 88 feet, what is the width? Okay. Okay, so Jesus has 74 feet. Okay. Okay. Thanks, Noreen. Okay, so we draw this picture here just to get an idea of what we're looking at. Okay, and we know that the area is everything. And then the way we find the area is to multiply the length times the width. So we've got an area of 6,600 square feet. We have length of 88, and now we just simply got to find W, which is the width. So we can do that by dividing both sides by 88. And then that's going to give us 75 feet for our width. So great job, guys. You guys did an excellent job solving that problem. Okay, so here we have a figure below. It's a parking lot. And we need to know how much pavement will be needed. Okay, so since it's not want to know how much pavement, this is going to be an area problem. So we multiply the length times the width. Now, if we wanted to know how much chain would need to be to surround it, then that's going to be a perimeter problem. Okay. Notice how the units of measurement are different for the area. For the area, we have square yards, and for the perimeter, we just have yards. Okay, that's a really big thing. Okay, and so we're looking at a similar type of problem here. When we walk around the field, walking around the field, once again, that word around the field means perimeter. Covering the pavement, the inside of the field, means area. Okay, so we're going to let this be our last problem. Then we're going to call it a day because it's 4 o'clock. All right, so here's our problem. The length of a rectangle is 5 times its width. If the perimeter of the rectangle is 96 meters, find its area. Okay, so yep, you guys are trying to find the area. Okay, so Joe has 280 square meters. So that's 280 square meters. Okay, what does everybody else think? Okay, so how's everybody else coming along? Okay. As you're working this, I went ahead and underlined the information that I use to pull two equations out of this word problem. The length is equal to 5 times 5w. Is means equal. And then the perimeter of the rectangle, I know what the formula for perimeter is. P equals 2L plus 2W is 96. Okay, so let's go through it. All right, so P is clearly going to be 96. Now, in order to work this problem, you can't have two variables. You can't have L and W. That's going to be a linear equation with two variables. And we know what happens when you have a linear equation with two variables. You end up having two ordered pairs, and you end up having not two ordered pairs, you end up having multiple ordered pairs that you have to graph. So in order to solve this problem, we're going to have to substitute in for L 5W so that we can end up with only one variable, which is going to be W. So we're going to take out the L and we're going to put in 5W. Okay. Now where did that 5W came from? It came from up here. We said that L was equal to 5W. Okay, so if two things are equal to each other, you can replace one with the other. Much like a $20 bill is equal to four $5 bills. So if you went into the store and you needed change, then they can take your $20 bill and give you four $5 bills for it. Okay, and you're still going to have the same amount of money. So that's all we did. We changed out the L for 5W. All right, you too, Lionel. Okay, and so now we got 2W here. Okay, so here we've got 2 times 5 is going to give us 10W plus 2W here. And then that's going to give us 96. And then we're going to add the 10 and the 2 together and come up with 12W. And from there, we can say 8 times 12 is 96, or we can divide both sides by 12. Okay. So W is going to equal 8. Okay, so that's what the width is. Now, in order to find the area of anything, it's got to be the length times the width. Okay, so we know what the width is. The width is 5. We still don't know what, I'm sorry, the width is 8, you know. We still don't know what the length is. Now, in order to find the length, we can come back to we can come back to this right here. We can take out the, we can take out the W and put in 8 in its place. And then that's going to give us L is equal to 40, like that. And so then from there, we're going to have A equals 40 times 8. And so our final answer is going to be 320 square meters. Okay, because we have 5 times the width will give you the length, and 5 times 8 is 40, and 40 times 8 is 320. So that's going to be our final answer, 320 square meters. All right, we've did more than stay past the time that we were required. I want to apologize for that. You know, typically I try to get out at 4. I realize that your time is precious and important, and that, you know, you got more classes to take than just math. So, you know, I'm sorry for, you know, not getting through the material as fast as I should have. I am going to archive the session. I'll upload it tomorrow and provide you guys with a copy of it tomorrow. Feel free to use it as you're going through and completing the remainder of your assignments. Okay, I'm going to stick around for a few minutes if anyone has any questions, but I'm going to stop the recording right now.